the very first chapter of maths, numbers. The whole chapter of numbers can be divided basically into three parts. First is definitions and classification of numbers. First part, definitions and classification of numbers. Second part, factors, or you can also say factorization, which will include factors, number of factors, how to find factors, how to find pair of factors, LCM, HCF, applications of factors, and also the sum of factors. And the third part is remainders and its applications. Alright, so first we'll take up definitions and different types of numbers. First of all, what are the numbers? किसको बोलते हैं numbers? What do we call number, or what do we know as number? So numbers are basically used to present size, quantity, or to measure, okay? Or if we have measured or counted two things, we can compare them. To compare, we use numbers. For example, how many students are sitting in this class? The answer will be 30, 40, 50. Okay. If I say what is the distance between Baroda and Ahmedabad, the answer would be 110. Which room is bigger, this classroom or the other classroom? So what will you do? You will measure the length of the class. Let's say 40 feet. The other one is 50 feet. So the 50 feet is bigger, right? So this is 50, 110, 30. These are all numbers. Okay. Other situations, if a company does some business and you say that they have done a profit, so how will you calculate? You will use some numbers again. You will find some the total revenue, total collection that they have done, and the total expenditure that they have done. So the difference is positive. That means we say that there is a profit, or if the difference is negative, we say that there is a loss. So again, we are using numbers. Okay. Now here we'll stick to a little basic things only. Numbers can be primarily divided into two types: real numbers and imaginary numbers. Real numbers are those numbers which actually fulfill this purpose. Now I'll explain. You will understand that when you see what exactly is the meaning of imaginary number. So basically, real numbers are all useful numbers. So things which look like numbers and they're really useful. Okay. Those numbers which look like numbers but not useful as numbers. As of now, you just need to understand any number which is square root of a negative number is called imaginary number. For example, we all know the square root of 9, that is equal to 3 or minus 3. We'll see later the significance of these two things. As of now, just say that square root of 9 is 3. What about square root of minus 9? If it is square root of minus 9, you cannot find the square root of minus 9. Okay. What will you have to do? You will have to break it like this: 9 into minus 1. Square root of 9 will be, so this can be separated as we are aware about this rule. Root of a into b can be written as root of a into root of b. So we take these two things as a and b. We can take them as root 9 into root of minus 1. Now, root of 9 is 3. Root of minus 1 is just as it is, because you cannot find root of minus 1. You cannot find the value of root of minus 1. So because we cannot find anything for this further, or we cannot resolve this further, what we do is we take the first letter of the word imaginary. The first letter of the word imaginary, that is I, and we give this a name I. So this can be presented as 3i. So where I is actually root of minus 1. So I use this space. I stands for imaginary and it is equal to root of minus 1. Okay. That means I square is equal to minus 1. Okay. If you further square it, you will get I to the power 4, which is equal to 1. That's the maximum that you need to know about imaginary numbers. Other than this, that is not important for us. Okay. Now let's come back to real numbers. Real numbers are those which are very useful for us. Okay. Now, real numbers further can be divided into types. So as we are just saying that any number which is useful, they're all real. So real can be further divided into two types on the basis of their usability. or you can also say on the basis of their presentation. Okay. Real numbers can be further divided into two types, and from here actual work for us starts. One part is a rational number, okay, the other part is irrational number. Primarily, real numbers are basically divided on the basis of their presentability in terms of decimal value. For example, when I say 1 by 2, we know it is 0.5, 0.5, 1 by 4 it is 0.25. Okay. These numbers which have a definite decimal part are called rational number. So numbers which have definite, or you can say terminating decimals, they are called rational numbers. Okay. Suppose the number is not terminating. Okay, first I'll take some examples of definite or terminating decimals. 1 by 2, 1 by 4, 3 by 8, etc. Minus 2 by 5 also. Positive, negative, anything it can be. Suppose we have a number which is not terminating decimal. For example, 1 by 3. But you see 1 by 3 has a pattern. It is 0.3 and then 3 and then 3. It goes on like this. And we present it as a recurring decimal. We call them repeating or recurring decimals. Okay. So if the decimal is non-terminating, but if it is repeating or there is a pattern of digits, take another example. 1 by 7 is 0. If you go on dividing, it is 1, 4, 2, 8, 5, 7, and again 1, 4, 2, 8, 5, 7, again 1, 4, 2, 8, 5, 7. You can check it by actual division. Okay. This can be presented as 0.142857. We know that these 6 digits are going to reappear in the same order. So we just present them like this. We put a bar. The bar just shows that the entire group of digits below bar is going to be repeated in the same order. That's it, nothing else. Okay. So instead of writing all the digits, you just put a bar on these digits which are going to be repeated. So here only one digit is going to be repeated. Here 6 digits. The whole group is going to be repeated. So these are called recurring or repeating decimals. So the numbers which have either definite or terminating decimals, they are rational numbers. Similarly, the numbers which have non-terminating but recurring decimals. Recurring decimals. Recurring decimals are also rational numbers. One thing that is invariably common in both these things you see, they are all in the form of a ratio. So these are the numbers which have some definite decimals. These are the numbers that we have which have infinite decimals but there is a pattern. Or the numbers which do not have any decimal. Numbers not having any decimal part. Like 4, 5, minus 7. Okay. So all these numbers, or you can also call them full numbers, complete numbers. We have certain names for these also, but we'll talk about them later. So numbers not having any decimal, numbers having a terminating decimal, the numbers having a patterned decimal, or the numbers decimal in which the pattern can be identified. They are all rational numbers. What you can see that each of these numbers can be presented as a ratio. Right? Look at that. 1 by 2, 1 by 3, 4 by 1, 5 by 1. They're all a ratio. In fact, if you look at the first 5 letters of the word rational, that is a word a ratio. Okay. So in general, the definition of rational numbers is given like this. Any number presentable as P by Q. P by Q. Any number presentable as P by Q is a rational number. Alright. Now, as we know that for a fraction to be defined, the denominator, that's true for any fraction, denominator cannot be equal to 0. So we just add a condition here that Q should not be equal to 0. So this is the actual definition of rational numbers. So in general, a little more detailed, definite terminating decimals, recurring decimals, no decimal. Okay. Or all together can be simply said any ratio where P and Q are simple numbers, Q not equal to 0. The only thing is none of this P or Q should be irrational numbers. So we also need to know what are irrational numbers. Let's see. If we have a non-terminating decimal like this one, this is a non-terminating decimal, right? Why do we call this non-terminating? Because it doesn't stop, it goes on, continues till infinity. Okay. If there is a non-terminating decimal and it doesn't have a pattern, it doesn't have a repetition pattern, alright, then what do we say? They are irrational numbers. So let's try and understand once more. The numbers which have non-terminating decimal parts and they do not have any pattern, identifiable pattern also. Okay. there is no group of digits which repeats itself. So we can say that there is no pattern, right? Such numbers will be called irrational numbers. So first I will put the technical definition, which says the numbers which have or which are non-terminating. So numbers which are non-terminating and non-recurring decimals. That means after decimal it should go up to infinity and there should not be any recurring pattern also. Right? Such numbers will be called irrational numbers. For example, root 3. Now what is the value of root 3? The value of root 3 is 1.732 as you are aware. But you know that on squaring 1.732 you will not get 3. You get something like 2.99 something and so on. So what it means is the exact value of root 3 is not 1.732. It is even beyond that. Up to what? It is up to infinite places. That means if you go on, it will not finish, it will go on. Okay. So root 3 is a number which is non-terminating decimal and it does not have any pattern. For example, any number which is not a perfect square root of that number. Okay. Cube root of a number which is not a perfect cube. Okay. So such numbers are irrational numbers. Okay. Some known numbers like pi. What is the value of pi that you have heard? 22 by 7? No. 22 by 7 is a recurring decimal. Pi is approximately equal to 22 by 7. The exact value of pi is still a matter of research. Nobody has been able to find it exactly. Okay. It does not have a pattern and it goes on. The first 4 or 5 digits match 22 by 7 and hence that is taken as the value of pi. Okay, so remember, pi is an irrational number. Approximate value of pi that we use for our calculation purposes to make our life simple, we use 22 by 7 or 3.14. Okay. So first, real numbers, they can be divided into two parts, rational and irrational. What I'll do is I'll make it a shorter tree. Real can be divided into two parts, rational, irrational. Okay. Now, rational numbers can be further divided into types on this basis only. You see, this part was not having any decimal part and these two together were having some decimal. So on that basis, rational numbers can be further divided into two types, integers and fractions. So we can say the numbers which do not have any decimal part are called integers. The numbers which have some decimal part are called fractions. Technically, we can also say any rational number can be presented in the form p by q, where q not equal to 0. This is what we say about rational numbers. Now, suppose if q becomes equal to 1, that means the denominator will go away, only the numerator will remain. In any ratio, the upper part is called numerator, the lower part is called denominator. Okay, so if the denominator becomes 1, it will become an integer like this. Okay, fractions, q not equal to 1. So if the denominator is not equal to 1 in p by q, that means it has to be a fraction. Obviously, we always talk about the most simplified fraction. Okay, for example, if it was 8 by 2, you don't say that it is a fraction because it is not most simplified. It will be cancelled by 2 and will become 4 by 1. So hence it is an integer. So full numbers, complete numbers without any decimal, they are called integers. Okay, and the numbers which have some decimal part are called fractions. Further, fractions can be divided into two types, proper fractions and improper fraction. Proper fractions are those in which numerator is lesser than denominator, p less than q. For example, 3 by 7, 5 by 9. Improper fractions are those in which p is greater than q. So numerator is greater than denominator, p by q. Okay, so p is greater than q, that means 7 by 3, 5 by 4, for that matter any other number. Improper fractions can also be presented as mixed fractions. Mixed fractions. Now mixed fraction means one part integer and one part fraction. Like 7 by 3, I am sure you are aware about this. You can divide this so 2 times complete, one remaining, one remainder, so 1 by 3 can be presented as 2 integer 1 by 3 fractions. For example, 5 by 4 can be presented as 1 integer 1 by 4 fraction. Okay. Let's take another one. 12 by 5 can be presented as 2 2 by 5. So 2 integer, 2 by 5 fractions. So they are called mixed fractions. Okay. So real numbers, rational, irrational, detailed definitions. In short, rational numbers can be further divided into integer and fractions. Fraction two types. Come back to integers now. Integers can be further divided into, actually from here, these things that we are going to do, you're aware about most of them. Let's see. Integers can be further divided into three types. Negative integers, positive integers. What about 0? 0 is positive or negative? 0 is not positive, not negative. 0 has a very special place in mathematics. I mean, when there is nothing, we say it is 0. Hence, it is very important because nothing also means a definite situation. Okay, so when I say subtract 5 from 5, you get nothing. Nothing is absolutely standalone, a particular, a perfect situation that we need to understand. Okay, you cannot ignore 0 when it comes on its own. Alright, so 0, it is not positive, 0, it is not negative. So 0, if I relate it to feelings, positive, good feeling, negative, bad feeling, so 0 does not have any feeling. Alright, just joking. But yeah, so 0 is not positive, not negative. Okay. Now positive integers, what do you mean by positive integer? The smallest positive integer is 1, then 2, 3, it goes up to infinity. The set of positive integers, they are called natural numbers. I'm sure you have heard about natural numbers. Negative integers, the largest negative integer is -1, before that -2, before that -3, and they come from minus infinity. The set of negative integers, they do not have any special name. We don't call them unnatural numbers. No, we don't call them anything. They're just negative integers. Yes, positive integers, they have been given a one name. Set of positive integers are also called natural numbers. Okay. Now this, I said here, the smallest positive integer is 1. The largest negative integer is -1. So before going ahead, there is just one small thing that I would like to add. There is something called number line or real line. Now what do you mean by number line or real line? It is just a infinite length line in which we take one reference point and we name it 0, or we assign a value 0 to that reference point. On the right side of 0, we decided positive numbers to be placed, and on the left side, we decide negative numbers to be placed, and we grade them or divide them in equal parts. And these terminals that we get, we put them, or we assign these terminals to integers. 1, 2, 3, 4, 5, and so on. -1, -2, -3, -4, -5, -6, and so on. All the in-between numbers will be occupied by fractions or irrational numbers. Okay, now, so as you can see, these numbers, they belong to natural numbers. These numbers, they belong to negative integers. Here, there is basic theory of number line that any number will always be greater than any number on left of it. Any number will be greater than the numbers on left side. Okay. Any number will be smaller than the number on its right side. Okay. So a number on right side is greater than the number on left side. Just remember that like this. Okay. So here, -6 is smaller than -5. -5 is greater than -6. -4 is greater than -5. -3 is greater than -1. So like this, we reach -1, which is the greatest of the negative integers. Correct. Similarly, we start from 1. 1 is the smallest. Then 2 is greater than 1. 3 is greater than 2. 4 is greater than 3. 5 is greater than 4, and so on. So smallest natural number is 1. Greatest negative integer is -1. Alright. Just one thing I left here, that natural numbers and 0 together, they are called whole numbers. So set of whole numbers, it is just a combination of set of natural numbers as well as 0 together. So natural numbers and 0 together, the whole set will be called whole numbers. The whole set is called whole numbers. Anyways, this is just the name that is being given. Alright, so I think quite a bit of definitions we have done here. So here we have concluded most of the definition classification part. Still there are certain things that are left. I think there are 4 things that are left that must be coming to your mind. 2 things, that is prime number and composite number. I'll tell you that they are a part of natural numbers. What about even number and odd number? Where would they figure in this number tree? Even numbers and odd numbers, where would they come? Okay, now to understand both even and odd and prime and composite, we need to understand certain words very clearly. Okay, so we'll share those words and then we'll go to these 4 parts. First of all, what do you mean by saying factors or multiples for that matter? If I say, what are multiples of 3, say? What are the multiples of 3? You may say many things, but basically the correct answer would be multiples of 3 means the numbers which appear in the table of 3. So 3, 6, 9, 12 and so on. Alright? Some of you may say minus 3, minus 6. Let's hold for some time in this. What about factors of 12? 12 is a number. Factors of 12. Now, what is the meaning of factor? The number which divides 12. Right? The number which divides a given number is called a factor of that number. So, factors of 12 would be. So, what do you have to think? What are the numbers which will divide 12 completely? So, 1, 2, 3, 4, 6 and 12. That's it. Some of you may say, why not minus 2, minus 3 and so on? They can also divide 12. Because you can always say, why was 3 a factor of 12? It was 3 into 4, hence both 3 and 4 were factors of 12. So why not, we can say that minus 3 into minus 4, because we know that a negative number into negative number will result in positive. So we may say that minus 3 and minus 4 are also factors of 12. Alright? Now here I'll mix another thing. Have you heard about something called prime numbers? I am sure. Now what are prime numbers? The numbers which are not divisible by anything. That is the way of saying. Actually they are divisible by what? They are divisible by only 2 factors. Divisible by only 2 numbers. Remember? I think most of you would be aware about this. If you are not, no problem. Prime numbers are those numbers which are divisible by only 2 numbers. Give an example. Let's say 7. What are the numbers which will divide 7? You'll say 1 and 7. That's it? Sure? First, are you sure about the definition of prime numbers? And then, are you sure about these are the only factors of 7? Answer is yes in both the cases. Definition of prime, only 2 numbers which divide the prime number. And factors of 7, 1 and 7. That is also true. We did not consider minus 1 and minus 7. You can see minus 1 into minus 7 will become 7. But we did not consider it. Reason is very clear. The words multiple and factors. These words are used only for positive numbers. By definition, by default, they have been defined in such a manner that these 2 numbers are used only for positive numbers. Okay? And they themselves are also positive. So first, they are defined only for positive numbers. Second, they themselves are positive. For example, while I said this, you may come up with the idea that what about minus 12? Now minus 12 is a negative number. So it will not have a multiple or a factor. Right? See, minus 2 is a product of minus 3 and 4. For that matter, it is also a product of 3 into minus 4. Or 2 into minus 6. And so on. Many other possibilities. These are all a simple product. This is a simple product of 2 numbers. This is a simple product of 2 numbers. Simple product of 2 numbers. What I am trying to say here is, every product may not give you a factor. Okay? A product will give a factor only when both the parts or all the parts of that product are positive. And the outcome is also positive. I think this makes things very clear. That factors or multiple words will be used only for positive numbers. So we'll say that minus 12, we do not talk about factors of negative numbers. Hence minus 12, we don't say that there is a factor of minus 12 or a multiple of minus 12. Okay, we do not talk about factors of minus 12. That's it. That's the only way to say it. Right? If the question says in how many ways minus 12 can be presented as a product of 2 numbers, so 1, 2, 3, 4, 5 and so many other possibilities you can write. Okay, that's what you need to understand. Otherwise, come back to this. Prime numbers, the numbers which are divisible by only 2 numbers. 7, factors 1, 7 and not minus 1, minus 7. Come back to this. Multiples of 3, correct 3, 6, 9, 12 and not minus 3, minus 6, minus 9. Factors of 12, 1, 2, 3, 4, 5, 6, not minus 2, minus 3 and so on. So these are the definitions of the words, factors, multiples and so on. Still, the question of even odd is still there. Where would they be placed? Or what do they have to do with these things that we just did? I'm sure you must have heard the definition of even numbers as the numbers divisible by 2. Yeah, right? Yeah. But the problem is, when I say numbers divisible by 2, that means we are talking about multiples of 2. The moment I say multiples of 2, that means we are sticking to only the positive side. So first, I'll tell you the examples of even numbers and odd numbers. Okay, first of all, even and odd are parts of integers. We have already seen that the integers can be divided into 3 parts, negative, positive and 0. Integers can also be divided into 2 parts, even number and odd numbers. Okay. Integers can also be divided into 2 parts, even number and odd number. Now, even number, first of all, I'll give you the examples. The examples of even numbers are 0, 2, 4, 6, 8, 10, 12, minus 2, minus 8, minus 12, minus 18 and so on. So first you need to understand the positive, negative, 0, all of them can belong to even numbers. Similarly, now see integers, ध्यान से अगर आप देखो that out of this, the 0, 1, 2, 3, 4, so 0, 2, 4, these are all even numbers. Okay? Whatever is left, whichever number is left here, they will all belong to odd numbers. So I'll put them all here. 1, 3, 5, 7, 9, minus 1, minus 3, minus 5, minus 7. They are also odd numbers. What I'm trying to say here is that even numbers and odd numbers, they belong to both positive and negative integers. What we have done, what we have studied till now in our school studies, that these are even numbers, these are odd numbers. We have always ignored negative numbers. Negative numbers are also part of even and odd numbers. Alright, so if you look at this carefully, every integer is either a part of even number or a part of odd number without any exception. Okay, now how do we define them? We can't say that multiples of 2 because multiples of 2 will not include minus 2, minus 8. Similarly, we can't say that 1 above or 1 below the multiples of 2 because multiple word cannot be used for negative numbers. We have to include negative numbers, so what we'll use? The word product, just now we said. So any number which can be presented as a product of 2 with any other integer. Any number which can be presented as a product of 2 with any other integer is even number. Similarly, 1 above and 1 below this number, 1 above and 1 below this number is an odd number where n belongs to integers. There is a presentation for different sets. I'll tell you in some time. But yeah, right now, any number which can be presented in the form of 2 into n is an even number when n is in integer. Just think about it. If n is 3, so 2 into 3 will become 6. 6 is an even number. If n is 4, 2 into 4, 8 is an even number. If n is minus 7, so 2 into minus 7, that is minus 14, that will be an even number. If you put n equal to 1 here, so 2 into 1, 2, plus 1, that is 3, is an odd number. 2 into 1, minus 1, that is 1, that's an odd number. If you put n equal to 5, 2 into 5, 10 plus 1, 11, that is an odd number. 2 into 8, 16 plus 1, or 2 into 8, 16 minus 1, those 17, 15, these are all odd numbers. If you put n equal to minus 4, so 2 into minus 4 is minus 8 plus 7, plus 1, that is minus 7, that is an odd number. 2 into minus 4, that is minus 8, minus 1, that is minus 9, which is an odd number. Okay, just remember this. So integers can also be divided into 2 parts like this, even number and odd numbers. Okay, now we have prime and composite numbers. Now where do they belong, or which set do they belong to? They actually belong to set of natural numbers. Natural numbers are divided into 2 types, prime numbers and composite numbers, on the basis of the factorizability of the number, on the basis of number of factors of the number. Okay, so prime numbers are those, we have already seen prime numbers are those natural numbers which are divisible by exactly 2 numbers. Okay, what are those 2 numbers? 1 and itself. So in proper words we can say that the numbers having exactly two factors. And what are those two factors? 1 and itself. Be very clear that it has to have two distinct factors. Two distinct factors. That's a very important condition. Now, composite numbers, the numbers having more than two distinct factors. Okay, so you can say that numbers which are not prime are composite. Is that so? Let's see. What about 1? So if you see 1, in case of 1 and itself become same. So there is this condition is violated. So what does it mean? If I say 1, the factor of 1 is only 1. So it does not have two prime factors or two factors. Right? It does not have two factors. It has only one factor. So it cannot be put in the category of prime. Composite numbers having more than two factors. All the more difficult for 1 to go into composite numbers. So 1 cannot be a part of prime numbers. 1 cannot be a part of composite numbers. So where do we keep 1? 1 is the king of natural numbers. So 1 will be kept here. So remember, 1 is not prime number. 1 is not composite number. Right? It is just non-prime, non-composite, natural number. That's it. Right? You have to be very carefully understand these facts and memorize them. Okay. Now the next challenge is to identify, how to identify whether a given number is prime or not. So what are the prime numbers? Let's take some examples. What is the first prime number? The first prime number is 2, then 3, then 5, then 7, and so on. Right? What about the first composite number? So 1 is not prime, not composite. 2 is the prime number. 3 is the prime number. 4. What are the factors of 4? 1, 4, and then 2. So 3 factors. That means 4 is the first composite number. Next composite number would be 6, then 8, then 9, then 10, then 12, and so on. Right here, 2, 3, 5, 7, 11, 13, 17, and so on. I hope you can see that there is no simple pattern for prime numbers or composite numbers for that matter. There is no simple pattern. Okay, be very careful. Here, the consecutive. Here, difference of 2, difference of 4, again difference of 2, again difference of 4, then 19, then 23, then 29. So 6 ka difference. So there is absolutely no pattern. Okay. So there is definitely no pattern for prime numbers or composite numbers. Right. One question can be, how many prime numbers are there in the first 100 natural numbers? So let's count prime numbers in the first 100 natural numbers. Okay, so what I've done is I've divided into the groups of 10. Let me say, in the first 10 numbers, what are the prime numbers? 2, 3, 5, 7. In the next 10 numbers, what are the prime numbers? 11, 13, 17, 19. In the next 10 numbers, you can check. How would you check? I'm sure one that you are aware. The other thing would be that you can check the divisibility. You know, whether a given number is divisible by any of the other numbers or not. If it is not divisible by any of the other numbers, that means it is a prime number. As simple as that. For bigger numbers, we have method, but for smaller numbers, we should know, or we should just use tables to find. Yeah, and that's why I'm saying it is very important to identify all the prime numbers from 1 to 100, and keep them in your mind. I mean, they're like your name, address, phone number, like that. Okay. So 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37. So 1 to 10, 11 to 20, 21 to 30, 31 to 40, then 41 to 50, 41, 43, 47, then 51 to 60, 53, 59, then 61 to 70, 61, 67, then 71 to 80, that is 71, 73, 79, then 81 to 90, that is 83 and 89. And very interestingly, from 91 to 100, there is only one prime number, and that is 97. Some of you may come up with the idea of 57 or 51 for that matter. Then you have 87, 91, 93. 93, it is shouting loudly that I'm divisible by 3, if you can see that. There is 9 and there is a 3. Zor zor se chilla ke bol raha hai, main 3 se divisible hu. To ye to nahi hona chahiye. 91 is in table of 13. 13 sevens are in 91. So it is not a prime number. Rest of the three numbers you can actually check the divisibility of 3. Are you aware that divisibility of 3 is dependent on the sum of digits of the number? What do? You add the digits. Say 51. If you add the digits, 5 plus 1, that is 6. If the sum of digits is divisible by 3, then the number is divisible by 3. So 51 is divisible by 3. 57. 5 plus 7, that is 12. 12 is divisible by 3. So 57 will also be divisible by 3. 87. 8 plus 7, that is 15. 15 is divisible by 3. For that matter, 9 plus 3, 12, that is also divisible by 3. So all these numbers are divisible by some or the other number. Hence, they are not prime numbers. Okay. Now, if we count them, in the first 10 numbers, how many prime numbers are there? 4. In the next 10 numbers, how many prime numbers are there? 4. Next 10 numbers, there are 2 prime numbers. Next 10 numbers, there are 2 prime numbers. Next 10 numbers, there are 3 prime numbers. Next 10 numbers, there are 2 prime numbers. Next 10 numbers, there are 2 prime numbers. Next 10 numbers, there are 3 prime numbers. Next 10 numbers, there are 2 prime numbers. Next one, the last one, there is only 1. Okay. So if I make the series, it is 4, 4, 2, 2, 3, 2, 2, 3, 2, 1. So in this manner, you understand, these are number of prime numbers in a decade. If I can use the word decade for 10 consecutive natural numbers like this. Okay, so in every 10 numbers, so first 10 numbers there are 4 prime numbers. Next 10 numbers there are 4 prime numbers. The next 10 numbers there are 2 prime numbers. In the next 10 numbers there are 2 prime numbers. Then 3, then 2, 2, 3, then 2, 1. So it becomes actually rhyming 4, 4, 2, 2, 3, 2, 2, 3, 2, 1. Now, what is the total number of prime numbers from 1 to 100? Either you add these numbers or you count actually from here. Whatever you do, you get 4 plus 4, 8, plus 2 plus 2 plus 3, that is 7, 15, plus 2 plus 2 plus 3, that is 22, 24 and 1, 25. Or you can simply count 1, 2, 3, 4, 5, 6, 7, 8 and so on. So there are a total of 25 prime numbers. So total 25 prime numbers from 1 to 100. That's what we said. The first 100 natural numbers. First 100 natural numbers means from 1 to 100. So there are a total of 25 prime numbers from 1 to 100. Are we clear in this? There are a total of 25 prime numbers from 1 to 100. How many composite numbers are there? Can somebody tell me how many composite numbers are there from 1 to 100? Check karo. So I think 75, and I'm sure you are wrong. That it cannot be 75. Why? How many numbers are there from 1 to 100? 100. Out of them, 5 are prime numbers, and there is one number, 1, which is neither prime nor composite. So when you go on counting composite numbers, what you have to do is number of composite numbers. If I say composite numbers in the first 100 natural numbers, what do we have to do? We have to remove something from 100. What all do we have to remove? Total 26 we have to remove. Why 26? 25 prime numbers and 1 which is not prime, not composite. Total 26 numbers have to be removed. So the answer would be 74 numbers. So from 1 to 100 there are 74 composite numbers. So 25 prime numbers, 74 composite numbers and 1 which is not prime, not composite. Okay. So this is how we check whether a given number is prime or composite. Right? For smaller numbers, tables and small divisibility tests will help you. For larger numbers, how can you identify whether it's a prime number or not? First of all, in your examination, difficult numbers wouldn't be asked. I'm not saying that this question cannot be asked. Questions will be asked. Bigger numbers may be asked, like which of the following is not a prime number, and there will be prime numbers, or there will be numbers of 6 digit, 7 digit, 8 digit. Trust me, you will have to only use divisibility test. You are not required to know more than 2 digit or 3 digit numbers. So don't worry about it. Right? It will be simple. You just have to check the basic divisibility of that number by smaller prime factors like 2, 3, 5, 7 and so on. Okay? That we'll see when the questions come. As of now, at least for 3 digit numbers, because if you remember tables till 10, you have already covered till 100. Okay? And a little bit, if you have done, let's say, a table till 15 or 20, 10 times wala table, you will be able to cover at least numbers till 200. Okay. But if there is a slightly bigger number but less than 1000, only 3 digit numbers, and we have to check whether it is prime or not, there is a method for it. I'll explain the method now. First, I'll explain the basis of the method. Let's say 120. Let's break 120 as a product of two natural numbers. It is 1 into 120. Now, there must be other possibilities also. As you can see, 120 is divisible by many other numbers. First thing that you need to know that any number which divides the other number, it cannot be alone in that process. For example, 1 divides 120, or we can also say 1 is a factor of 120. What did I say? 1 cannot be a factor of 120 alone. There has to be another factor of 120. Similarly, 2 is a factor of 120, but it cannot be a factor of 120 alone. There has to be another number which is 60. So first thing, factors are always cofactors. They always exist in pairs. Okay. Then 3 into 40. Then 4 into 30. So what are we doing? We're just trying to all possibilities of these pairs. One thing you can notice, we are increasing the first factor. We started from the lowest possible. Now we have only way we can go is up. Here we started from the largest factor and the only way we can go down. Can you see that the factors are becoming equal now? The parts are becoming equal or proceeding towards becoming equal. Next possibility is 5 into 24. So this one has increased, this one has decreased. So slowly they are moving close to each other. 6 into 20. 7 will not divide 120. No, you go on checking whether it divides or not. Like 8. 24 is divisible by 8. So you would know just by looking at this. 40 is divisible by 8. So 8 has to be a factor alone also. Now 8 के case में क्या बन जाएगा? 8 5 is 40. So 5 into 3. 15 will be the other factor. Or you can divide 120 by 8. Right? 9. 9. No. 9, it won't be divisible by 9. It is divisible by only 3. 3 into 40 say, you will be able to know that it is not divisible by 9. Why? There is already a 3. 40 is not divisible by 3 because for 9 you need 2 3s. So it is not divisible by 9. Then 10 into 12. Then 11, it will not be divisible by 11. Then again 12. So the same pair will repeat. So after that you don't need to go. Now, as I said, no factor can be alone. No number can be a factor alone for a given number. Right? They always have to be in pairs. Right? Now just understand one thing, and I'll make certain statements. Is 24 a factor of 120? If the answer is yes, what is the reason of that? One of the very important reason is because 5 is also a factor. Because together by multiplication they make 120. Right? You know, if there was a situation, had 5 not been a factor of 120, 24 cannot be a factor of 120. Try and understand this. If 6 was not a factor of 120, this 20 cannot be a factor of 120. Right? So for all of these larger numbers, it's imperative for these numbers to be a factor of 120. Clear? Okay. Now that means if at all we have to check about a factor of 120, we don't need to go for bigger numbers. We only just need to check the smaller numbers. That's point number 1. Up to what? Up to a situation, only up to this situation where they are tending or they are almost equal or they are tending to be equal. If you look at this closely, close to 120, what is the perfect square? 121? That would have been 11 into 11. Oh, right. So we needed to check only up to the square root of this number. Okay? You know, when they become almost equal, let's say, suppose if there was if 120 could be written as x into x, I think one thing that is very sure that x is greater than 10 and this x is lesser than 12. That is absolutely clear. दोबारा बोलता हूँ. If it was possible to write 120 as x into x, if it was possible, one thing is very sure that x is more than 10 and x is less than 12. Acha. Now if you do not understand this, let me say that 120 is equal to x square. Very clearly, if x was 10, its square would have been 100. If x was 12, its square would have been 144. Now this is 120, so it has to be between 10 and 12. Alright, that's what I'm saying. So x is root of 120. Now this root of 120 has to be between 10 and 12. Now why I'm saying this, once you find the root of that number, approximate value, you don't have to find the exact value, approximate value, then only check the numbers which are smaller than the square root of that number. Check what? Whether this number is divisible by any of those numbers or not. Let's take an example. I'll give you an example, it's very easy to understand. Let's take 160. Check 160 whether it is divisible by 161, whether it is a prime number or not. Okay. First thing, take square root of 161. Do not calculate the square root. Alright. Look at these squares which are around 161. Like 12 square is how much? 144. 13 square is how much? 169. Oh, this is 161. So this number will be 12.5 or 6, something like that. Don't have to be exact. Just andaze ke liye. Now, less than 12.56, what are the natural numbers? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. These are the only numbers. In fact, 12 also, because 12 is less than this number. What I'm saying is check whether 161 is divisible by these numbers or any one of these numbers or not. Okay? Check whether it is divisible by any one of these numbers or not. Right? Now see. 1 you don't need to check. Why? Because 1 definitely is a factor of every number. 2 you need to check, 3 you need to check. A number for divisible by a number, if it is divisible by 4, first of all it has to be divisible by 2. So we don't need to check for 4 separately. Similarly, we don't need to check for 6 because 2 or 3 we would have already checked. 8 we don't need to check because 2 we would have checked. 9, 3 ki wajah se 10 we don't need to check. 11 yes, 12 you don't need to check. Now basically if a number is divisible by 2, if it has been proven, so whether it is divisible by 4 or not, it wouldn't matter, right? So what you need to do is you need to check only by the prime numbers below the square root. Okay? So what is the method? Once again, listen very carefully. Whatever number you have to check, take square root of that number, approximate square root of that number. Take the prime numbers below this. Prime numbers below 12.56 or whatever it is. Now what are the prime numbers below 12.56? 11, 7, 5, 3, 2. Now check whether 161 is divisible by any one of them or more or not. Because if it is not divisible by any one of them, then it is a prime number. If it is divisible by even one out of these 5, it is not a prime number. Okay, now let's see. It's very easy to check for 2 and 5. You only have to glare on the number. Okay, just look at it very closely. 161, the last digit is 1. So it is not divisible by 2. Because the divisibility test of 2 is check last digit. Check last digit should be 0, 2, 4, 6, 8. Divisibility test of 5 is check last digit should be 0 or 5. So this number is not divisible by 2, not by 5. Check divisibility by 3. For 3, what you need to do? Just check the sum of digits. So 1 plus 6 plus 1, that is 8. So this number is not divisible by 3. Alright? Now similarly, check for 11 and 7. If you know the methods, I'll discuss about the divisibility test of 11 and 7 in some of the later sessions. But as of now, divide by 11, divide by 7. Now 11, it won't be divisible. 11, 121 plus 40. You know, so 161 is 121 plus 40. This is divisible by 11, this is not. So this number is not divisible by 11. Similarly, 7. So 161 is 140 plus 21. Or you just divide. So 140 is divisible by 7. 21 is also divisible by 7. So 161 has to be divisible by 7. Oh. So 161 is divisible by 7. Hence, it is not a prime number. It is a composite number. I'll be clear on this. So 161 is a composite number. You can always pause, play back, check the method again. I'll give another number, let's say 293. We have to check whether it is a prime number or composite number. So what do we need to do? We just take square root of 293. Again, do not calculate the square root of 293. See if there is any square close to 293. So 12 square, 13 square we have already reached. Oh, 14, 15 square is 225, 16 is 256, 17 square is 289. That means root of 293 will be equal to 17.1 or 2, something like that. Okay. So take prime numbers below this square root. So what are the prime numbers below this square root? 17, 13, 11, 7, 5, 3, 2. These are the prime numbers below this. Okay. Now see. Is this number divisible by 2? No. 5? No. 3? 2 plus 9 plus 3? No. 7, just divide. This 7 ke liye what you can do is 280, the nearest number which is divisible by 7 to 293 plus 13. Now 280 is divisible by 7, 13 is not. So this number cannot be divisible by 7. Same logic for 11, 220 plus 73. Why I am breaking like this? Because isme kya fayda hai that one number is a multiple of 10. It's easier to subtract or add. Okay, so we are breaking 293 like this. So 220 is divisible by 11, 73 not divisible by 11. So 293 is not divisible by 11. Now 13, 260 plus 33. 293 can be written as 260 plus 33. 260 is divisible by 13, 33 is not. That means that number is not divisible by 30. Here we go. 17 is already we just drew that logic that it is 289 plus 4. This is square of 17. This is not. This is not divisible by 17. So this number is not divisible by 17. What does it mean? 293 is not divisible by any one of these numbers. What did we do? We took the square root of that number, approximate square root of that number. Then we considered the prime numbers below the square root of that number. And then we checked whether the given number is divisible by any one of those prime numbers or not. It is not divisible by any one of them. So what do we say? 293 is a prime number. So this is how we check prime numbers and composite numbers. Alright. So now this is where we have completed the definitions, classifications, number of ways of checking and other things. I'll just give one more question to end the session. Find number of zeros at the end of the product of first 50 prime numbers or first 5000 prime numbers. Number of zeros at the end of any product. First of all, how would you find the end digit for any product? Let's take an example. 273 into 548. You can multiply and find. But to find the unit digit or the end digit, you just need to multiply the last digit of these two numbers. So 8 3s are 24. So 4 will be the answer. If I just want to know the unit digit of a multiplication, we just take the unit digit of each number and we multiply. That's it. Now, how would you get 0 here? You may get a 0 if at these two places, if any one of them has a 0 here, you will get a 0. Like 270 into 548. Obviously, it will come 0. You'll have a 0 in the end. The product will have 0 in the end. But the prime numbers never have a 0 in the end. So, that possibility is gone. What is the other possibility? See, 2 into 5. How much is it? 10. So, in the product, 0 will come in the last place. 0 will come in the end. Okay? This is the only other way of finding a 0. This is one way of 0. Like one of them is 0 or both are zeros. And the other way is one digit has 2 and the other digit is 5. So, 2 into 5 is 10. So, in the product, in the end, we will have a 0. Now, is 2 a prime number? Yes. Is 5 a prime number? Yes. This is the only possibility which will yield a 0 for a multiplication. Now, if I try to write the 5000 prime numbers, which number would I start with? The first number would be 2, second one would be 3, next one would be 5, next one would be 7, and so on. Do I really need to go further? No, because there is only one pair of 2 and a 5 that is there in this. No next number, none of them will be divisible by 5 or 2, right? That means there is only one possibility of a pair of 2 and 5. You know, we can always write it as 2 into 5 and then all other prime numbers. See, please understand that whether you take 50 numbers or 500 numbers or 5000 prime numbers, this part is not going to make any difference because that will not have a 0 in the end in the product. Alright? Because 0 will come only because of 2 into 5. And there is no other prime number which is a multiple of 5 or a multiple of 2. No other prime number which will be a multiple of 2. It can't be a multiple of anything for that matter. Alright? So there will be only one 0. So it is like 10 into a number n. So product of this whole thing. And that n, we know for sure that it will not have a 0 in the end. Right? Because all these things will be 3, 7, 9. You know, you must see that other than 2 and 5, every other prime number has to end in either 1 or 3 or 7 or 9. All the other prime numbers other than 2 and 5 will always end in either 1 or 3 or 7 or 9. Why? Because if they end in 2, they will be divisible by 2. If they end in 5, they will be divisible by 5. So they will not remain a prime number. Okay? So they have to end only in 3, 7, 9 or 1. But their product will not have a 0 in the end. So 10 into n, whatever it is, there will be only one 0 in the end. So the answer is 1. What was the question? Number of zeros. So the answer is 1. Right? Just try and understand. Repeat the video once again. Or I'll just repeat a little bit. A 10 can be created only by a product of 2 and 5 if it comes to prime numbers product. Out of the given prime numbers, whatever you do, there is only one 2 and there is only one 5. So there will be only one pair of 2 and 5 that is possible. Hence, there is only one 0 that is possible in the end of this product. Okay. So in this first session, we have done the classification and definitions of different types of numbers. Okay. The other two parts we'll take in different sessions. Right. So thank you so much. That's it for today.